Markov chains and stock prices. I'm going to go through what a Markov chain is, how it can be applied to a basic stock price model, and the sorts of information that Markov chain models allow us to extract from our data. Stock prices for a basic model can be put as thus. We have stock prices over time. We convert them to stock return data by subtracting the current day's closing price from the previous. And as a result, some of the days will be positive, some will be negative. On the positive ones, we can say that those days are going to be up, and on the negative, we'll say they're down. So we're basically just in each row of the data set, replacing the actual values with just values of U and D, making it nice and easy and simple, thus giving us what is known as a stochastic process, finite state stochastic process to be more precise. Finite because there's only two states wherein we can find ourselves, down or up. This is what is called a state diagram, and it allows us to understand how the process flows or where it flows over time. In this case, I have two states that a stock can be in, down or up. If the stock closed down, it could close the next day down, or it could leave and close the next day up. Vice versa, if it already closed up the following day, it could close down, okay? Or it could close up again. So those are sort of the four possibilities that we have here. This is what is known as an aperiodic Markov chain, meaning I can reach every state immediately from every other state, and I don't need to wait a certain number of times for the process, or in this case, the stock, to enter back into another state. In other words, it's entirely plausible that one day the stock can be up and the next it's down, in plain English. As a result, Markov chain models are usually computed in terms of what are called conditional probabilities or transition matrices rather than outright probabilities. So the basic model is as follows. We take the ups and downs and we compute a lagged table where we take the up and down and shift some of that there, and we now have a whole bunch of ups and downs. As a result, we're able to hold steady what happens the day before and kind of compute conditionally the chances or the probabilities that I'm going to end up in one of those two other states. Alternatively, the way that I can get to those probabilities, by the way, is just by computing a basic contingency table, which for all you Excel heads out there, is just a pivot table. Anyway, from the pivot table, you can compute the probability transition matrix. That's computed by noticing that there are 5 observations wherein the day before we were up, 3 of those were up, 2 of them were down in the following day. So therefore, the chances of the 5 days we observed, 3 out of 5 were up, 2 out of 5 were down. Of the 2 I've observed down, 1 out of 2 were up, 1 out of 2 were down. That's how we got those numbers there. From here, we can then use this matrix to solve for the probability of, on any day, the stock being up or down, which interpreted in this context simply means the proportions of days, assuming we did this out to an infinity number of days, what proportion of those days would be an up, what proportion would be a down. So here you have a certain proportion up and certain proportion down, and we are mandating that they equal 1. If you replace these with numbers and x and y, this would actually be a very simple problem from the 8th grade. You just solve. It's a system of linear equations. Step 1, solve the first 2 equations. Step 2, normalize out by using the 1. So solving those equations, you get 1/2 and 2/5, which normalizing just basically means add them together and divide each one by that. So we do just that. We add them together, 9/10, each one respectively divided by 9/10, and the normalized versions gives us 5/9 and 4/9. By the way, alternatively, we could have resolved or solved for those quantities by leveraging what is known as the Markov property, which basically just means that if I wanted to, if I had only this information, and I wanted to guess what the information for the next day would be, I'm going to ignore all the other information. And when I go to move on to the next day, I'm going to ignore all the information before. So when I go to guesstimate 2, I'm only using information from 1. When I go to guesstimate what's in 3, I'm only using information from in 2, ignoring what is in 1. This is what is called a memoryless property. And more specific to Markov chains, it's actually known as the Markov property. So, given that we have the Markov property, which basically means that the probabilities of the state we land in strictly are based on where we currently are, or the state wherein we currently find ourselves, if we leverage that property, this is actually true. Meaning that I can estimate those probabilities by taking the matrix, multiplying this matrix, multiplying itself multiple times, and taking that multiple times out to infinity. You can write some code to do that, which I did in R real quick. Here's the matrix, all right? The first way is actually by using linear algebra to solve for the eigenvalues of the transpose, which will then give you this result here. And if you look at those are the repeated decimal versions of these here. The second way to solve that same problem could have been very easily done by noticing that this is multiplying the matrix by itself multiple times, as you can see on that line right there. And you see you get the same exact quantities. So I've confirmed it 3 different ways: algebraic manipulation, over and over and over again, and actually a third approach using linear algebra, using what are called the eigenvalues. Once you have these steady state probabilities, which tell you that out of every 9 days on average, 5 of them will be spent on the up, 4 of them will be spent in the down, the question is how long, or another question I can look at is, how long do I need to wait? Assuming I started in down and it left, how long do I need to wait before it comes back? That's what is called the mean recurrence of a state, and it gives us some pretty interesting information about each of those 2 states. It tells us how long we have to wait, or how long we can expect the process to be out of that state before it re-enters. So, in plain English, here this is saying that if the mean recurrence is 2.25, if I was in the down and I left, I usually have to wait 1, 2, and a quarter of a cycle before it comes back into down. If I started in up, I usually will have to wait 1 and then 1/8 of a cycle before it comes back around to you. That information is pretty important because it tells us how long we have to wait for some of these different states to manifest before we enter a different manifestation of one of these states. In a nutshell, that is the Markov chain model applied to stocks and looking at it from a few different properties. As there are many more properties, we can actually extend this to what is known as Markov decision processes. I'm Miles Garvey. Follow me on TikTok, YouTube, and LinkedIn.